My name is James Guillochon. I'm a Einstein postdoctoral fellow at the Center for Astrophysics at Harvard. I got my PhD from UC Santa Cruz with my advisor Enrico Ramirez-Ruiz. I'm currently in my third year at Harvard, and the primary focus of study of my research is strong tides in astrophysics, and some of the strongest tides come from supermassive black holes. So when you're doing orbits around supermassive black holes, the simplest thing you can do is just treat them as being Newtonian. So the orbits would behave just as, say, Earth's orbit around the sun behaves. But that is, at best, a gross approximation. When you start getting really close to the black hole, the orbits start to deviate quite significantly, especially if the black hole is spinning. So determining the actual motion of matter around the black hole is critical for determining what happens to, say, the remains of a star after it's tidally disrupted by a supermassive black hole. So general relativity impacts the process by which the matter that is removed from a star in a tidal disruption is converted into light, which we can actually observe. So depending on how close the star comes to the black hole in its encounter, the rate at which the material circularizes can alter depending on how strong the relativistic effects are. And that comes as a result of the precession induced by the black hole's metric. And this, in principle, has direct consequence for the observational signatures of tidal disruptions. And in principle, you can actually use the observations we have to back out how relativity is working around these objects. So very recently, there was a claimed superluminous supernovae discovered by an observing team called Assassin. The original hypothesis was that this was, in fact, a very, very massive star that exploded. But recently, people have come to the conclusion that there's just not enough energy in a massive exploding star to produce this event. So now people have started to consider the option that it's the tidal disruption of a star by a very massive black hole, something on the order of a few times 100 million solar masses. And in those very massive black hole disruptions, relativistic effects are very, very strong. They cause the material to precess around quite wildly. And modeling that particular event, I think, is something very interesting, related directly to basically general relativistic effects. So, I think oftentimes where you can get a lot of benefit is being made aware of certain techniques or mathematical language for describing things that perhaps on your own you might have had a difficult time deriving from scratch. So examples of that might be engineers oftentimes have codes they use to simulate building bridges, and they use particular techniques for doing that. Some of those codes have actually been used recently in astrophysics to model colliding stars and other very highly energetic phenomena. So I think oftentimes, we're very myopic. We only focus on our topic of study, and oftentimes it can be very fruitful to just describe your problem to other fields, and sometimes that may bear fruit and other times it may not, but it really, I think, gives the potential for the greatest gains when you talk to someone who's doing something completely different from what you're doing.